Okay, thank you everyone for coming. So this is the last week of teaching. So today we'll just go over a sort of introduction to GPU programming. We'll go back to where we started at the beginning and talk about the actual hardware itself. And then on Thursday, the next session, we'll talk about the sort of nitty-gritty of programming these devices. So today, what I want to talk about is just first sort of introduce the actual GPU hardware, in case some of you aren't familiar with it. To talk about the sort of different options we have when we're programming for a GPU. To introduce a sort of array-based way of programming with a GPU. This is quite similar to how you would use like NumPy with Python, and you sort of abstract away a lot of the complexity and just call sort of generic array level functions. Okay, so this is the sort of picture that we built up last time actually at the start of the course. So as a sort of recap, you have the motherboard, which is the image in the center, which connects all of your different devices together. So you have some permanent storage in like a hard drive. You have some random access memory that sort of is your sort of working memory while you're processing things, and you actually have the sort of brain of the computer itself, the processor. But optionally, you could also have a graphics card. So this is like a separate device that you can add into your computer to sort of offload a few specialized workloads that can be processed more efficiently on a GPU over a CPU. So nowadays, the companies that create these GPUs tend to call them GPUs, which is like general purpose graphics processing units, because originally they started as specifically graphics oriented workloads. So sort of rendering sort of pixels to a screen on a game, or maybe it's from like an animation studio that's like rendering out their film or movie. But nowadays, they're used for a lot more than just those sort of specialist applications. So graphics, or you might buy a GPU and do no graphics work with it at all. So these sort of devices are aimed at sort of massive parallelism. So they're aimed to sort of work alongside the CPU, while the CPU is sort of general purpose and can handle most tasks. The GPU is more designed for specifically highly parallelizable workloads, especially graphics workloads. But nowadays, they're often used for other things. So they're really good at doing sort of big simulations. So like fluid dynamics and stuff can be offloaded to a GPU. Also, if you're doing any sort of machine learning or AI, these are almost essential to actually be able to get the results you want in a sort of timely manner. These are the standard for AI and machine learning. So the main difference is, while a traditional CPU, like the one in your computer, might have sort of 4, maybe 8 cores, some bigger desktops might have 16 or 32 cores. GPUs, at least the modern ones, have tens of thousands of cores, all working together. They have a slightly different structure, but the scales are orders of magnitude apart. So if we look sort of under the hood, if you look at a graphics card and take away all of the like heat sinks, this is sort of what you would see. So the one part that's quite important is at the bottom there's a connector that connects it to the motherboard, so it can communicate with your processor. And so these things work alongside each other to come up with a result. However, you'll notice these little sort of black chips scattered along the GPU itself. These are memory chips. So a GPU has its own memory that it works with. So you have your main memory, your RAM, which is separate to your GPU memory. And so if you were to actually see some sort of RAM chips and they have these little black dots, these little black squares on them, they're very similar. But this memory tends to be a bit more specialized for what a GPU needs. So like high bandwidth instead of optimizing like for latency. It also has its own power. So most of the the cylinders that you can see on the card are just capacitors. So it is essentially like a self-contained like computing unit. It has all the different parts on one chip. And finally, in the middle, you have the actual processor itself. So if we zoom in a bit or use a diagram of the processor, it can be a bit overwhelming to see what's actually going on here. So this is an image taken from a blog post NVIDIA did that sort of broke down one of their most recent cards, the A100. This is the card that's available in Sulis, the HPC that we have access to here, or one of the HPCs we have access to here. And in this diagram, I'll point out a few key points. So on the edges here, you have these sort of modules. These are the little black chips that were on the previous slide. There's basically just the onboard memory. So it's the memory that the GPU cores will have access to. Most modern ones use HBM2. This just stands for high bandwidth memory. So it's very high throughput. That's all you really need to know about it. But what you also notice is just like the CPU, the GPU also has a lot of cache on board as well. And we sort of spoke a lot about cache and how important it is for making sure you can compute at the speeds necessary, because memory tends to be a lot slower than your actual clock cycles of your CPU. So you need to be able to have some really fast cache to be able to feed the processors so as to not bottleneck your calculations. And then these sort of little blocks here are, on this diagram, they're not quite individual cores. This is like a group of cores together. So in this case, this is an NVIDIA card. They call them streaming multiprocessors. Most sort of graphics card makers have these sort of chunks of processors. So these contain multiple things. So again, zooming in once more, on the right, we have a diagram of one of these streaming multiprocessors. And you can see they have multiple cores throughout, and they have specialized cores for doing certain operations. So for example, you can see in sort of light green, the small blocks, FP32, this is 32-bit floating point operations. So it has a special part of the chip just for doing those operations. It has a part for integers, and it has a part for 64-bit floats. This is a modern GPU card, and so only the sort of higher end modern ones tend to have good support for 64-bit floating point operations. Because again, these originally were designed for graphics cards, and you don't really need high precision for graphics. Whereas if we're doing sort of scientific numerical workloads, we might need that extra precision. So it's just important to sort of check whether the graphic card can actually support double floating point precision, which is the 64-bit type. Also, these new cores have huge sections, which they call tensor cores. These are like specialized cores for doing operations like matrix multiplication, because these come up a lot in loads of applications, specifically AI. So these tensor cores are really good for accelerating AI applications. So again, also what you can see here is there's lower levels of cache. So each of these cores has access to some sort of shared memory. And hopefully what you can see from this is there are lots and lots of cores. So you can process lots and lots of instructions at the same time. But they're sort of suited more towards your typical sort of math operations. They're not as general purpose as what a CPU can do. A CPU is kind of like a jack of all trades. It can do everything, and it can do everything quite quickly. Whereas this is designed more for a specialized workload that is very high throughput. So you can do, if a task is highly parallelizable, you can do it on a GPU, and if it's relatively straightforward. Also, something to notice is each core has access to far less cache than a CPU core. A CPU core might have like 100 kilobytes of cache, like per core. This is the cache right next to the CPU. Whereas all of the processors you see here have access to around 200 kilobytes, and it's shared between all of them. So what each core does has to use sort of less memory as well. Okay, great. Don't worry if you haven't taken all of this in. This is a more abstract notion. We might need it a little bit more on next Thursday, but all I want you to take away from this is GPUs have lots and lots of cores, and that's what they're designed around. So we need to talk about some of the GPU platforms. So this is not the same as it's a very different world to CPU design. So CPUs, even if you get your CPU from AMD or Intel, they use the same instruction set, and so we largely don't need to think about the vendor, so the manufacturer of the CPUs that we're using. Even ARM chips as well, like the M1, the Apple M1 chip. A lot of the instructions for that are abstracted away for us as programmers. For GPU programming, it's a lot more important which vendor comes up. So I've already named one vendor, NVIDIA, which is the sort of main one. Does anyone know any other vendors? Any at all that make GPUs?
ATI?
Yes, so ATI is the old name for the company that used to make a graphics card that got taken over by AMD. So now we have AMD as well. So they're the sort of second biggest, but I should really stress NVIDIA have a vast majority of the market share, especially in HPC applications. So whenever you're using a cluster, it will probably be NVIDIA cards if it has GPUs at all. Should also mention that Intel are also trying to come into this and making their own GPUs. So I expect in the next few years, they'll start making some data center oriented GPUs as well. They're not quite there yet, but it will probably come out in the future. So I mentioned it just then, Apple makes their own silicon now, their own CPUs, and as part of their processor, they have some part to offload graphics to, and they use something called Metal it's like a programming interface to program these GPUs. So what I'm going to focus on today and also on Thursday is talking about CUDA specifically, which is the sort of hardware platform and programming model that you use for NVIDIA GPUs. Unfortunately, CUDA only works on NVIDIA graphics cards, and they've kept it quite closed, and it's very closed, so you can't run it on other platforms, unfortunately. But there are other options that you can use, and a lot of the skills are very transferable if you have to learn another framework, but just keep that in mind. So, so this CUDA is basically a sort of abstraction. It's a method that you can use to sort of program for a GPU without having to think about the exact specifics of the particular graphics card you have. So each year they release a new generation, and you don't want to have to rewrite all of your code to run on new GPUs. You want to be able to use your same code and compile it for the new graphics card and have it just work on there. And because from generation to generation, there's a lot more actual hardware changes under the hood than you would see on typical CPUs as well. So having this abstraction lets you write code that will sort of last a lot longer. So CUDA also includes a bunch of libraries written by the people at NVIDIA themselves that provide algorithms for doing your common stuff. So like BLAS, for example, which is your basic linear algebra subsystem. So your matrix multiplies, your dot products, sort of your generic operations like that. You also provides an interface for FFT, so fast Fourier transforms, which is also quite common, and they're quite hard to implement yourself efficiently. So they give you some implementations for that. Also random number generation and your typical math operations, so like sine, cos, like exponentials, have all been implemented in the existing CUDA library. They also have quite a few linear solvers as well. So for example, if you want to solve a set of simultaneous equations with like using a matrix, they have solvers for that as well. Also, if you do machine learning or AI, you'll probably have to install this additional CUDNN package, which does sort of deep neural network accelerations as well. Okay, so CUDA originally has an API for languages like C and Fortran, because typically that's what sort of high performance programmers tend to use. And so we want to be able to make use of the C API. So a few people came along and created a package called CUDA.jl, which sort of acts as a wrapper around the C API. So we can use the functions from C without having to sort of re-implement everything from scratch. So this CUDA.jl sort of sits on top of the C API. And essentially what that provides is some interfaces, some wrappers around the code so that we can use it natively from Julia. So the way it does this is it defines some special array types. So they're called CU arrays or CUDA arrays, so that you can choose which function, you can choose an implementation based on the array type. And they've also implemented some sort of basic functions as well. So if you say sum and you give it a CUDA array, it will use the CUDA version of the sum function or the reduction there. And it's the same for like broadcasting, mapping, sign, matrix multiply. It will just point it to the right place in the CUDA library for you. We'll see this in a lot more detail in a few minutes. So something that's also quite special about this, which is quite different from other languages, like Python, for example, is like Julia is compiled. It's just in time compiled. So that means that you can essentially write some bindings to directly generate your GPU machine code for you from the native Julia code. So we're not restricted to only using what's in the C API and having to write our kernels in C. We can just write what we need in native Julia. So again, Julia's compiler is called LLVM, and LLVM is like a way of allowing you to compile code to a lot of different backends, a lot of different devices, including GPUs. So essentially what happens is you can write some native code in Julia, use CUDA.jl's sort of compiler bindings, which then uses LLVM. LLVM then creates your device code to run essentially your native Julia code directly on the GPU without having to cross into another language at any point. Again, we'll see this in just a minute. So for the rest of this, we'll go over sort of a demonstration. There is a GitHub repository with all of the examples that we'll go through if you want to look at this now or after the lecture as well. Okay, we'll go through how we'd actually use CUDA. So the very sort of simplest, easiest way of using CUDA is to just change your arrays into the CUDA array equivalent type and write your Julia code using like your broadcasting notation. So when you actually add CUDA, so if you're in the Julia REPL and you type add CUDA, it will download the package for you. And also if you say using CUDA, if you don't have the CUDA libraries installed, it will download them for you at this point and install them, which is quite nice. You shouldn't have to leave Julia at any point to install anything else. You will need an NVIDIA graphics card and also the NVIDIA drivers installed, but if you have it in your computer, you'll likely already have the drivers. This command checks the version info, and it basically tells you what versions of all of the internal libraries that you have, and also which graphics cards you have available. So usually you'll see one device at the bottom, and it will tell you which device that is, which is good. If you don't see any devices here, that's probably a problem. You need to find a computer with one of these devices. On the website, actually, there's a link to a Jupyter notebook, which, at least as of a month ago, allowed you to spin up like a Jupyter notebook on Google Colab with a GPU enabled. and you can use Julia with it as well if you want to experiment. You also want to check whether CUDA is actually functional or not. You only have to do this like once on one machine just to make sure everything's working the way you expect. So hopefully this code will be very familiar. All we're doing is creating 3 arrays, A, B, and C, which are just vectors. A and B are just random numbers, and C is just allocating some memory using the similar function. And you'll note that we can use this broadcasting notation, so C dot equals A dot plus B to do element-wise addition. And the dot equals means that we're storing the results of the element-wise addition into the array C on the left-hand side. So the way this works on the GPU is, well, for starters, the GPU can only access memory that's on the GPU itself. And currently, these arrays are just on the host device. So we call the host like your main memory, the main computer. And so we need, before we can do any computations at all on the GPU, we need to copy the memory from the host memory, the CPU, onto the device itself. So CUDA provides this function CU, which basically converts an input array into a CUDA array. So if we run this command, you can see that now, right, so previously A was a vector of float 32s, or a one-dimensional array of float 32 values on the CPU. Now, when we use a CU function, what we do is we copy over that array onto the GPU itself, and the array type has changed. Now, instead of a normal array, it's a CU array, or a CUDA array. We can do the same for B. And now, for C, we can use the same similar command, the exact same function. We don't have to call a different function. And because the A GPU is of a different type, it will know to create the similar array on the GPU itself. So again, we run that and we get another CUDA array. And we notice, or hopefully you can notice, that this line 11, this broadcasting operation, is exactly the same as this next operation on line 18. The only difference is we're using the GPU versions of the arrays. We haven't changed any of the source code. We run this, it works just fine. It compiles, everything works great. So we just did a vector addition on the GPU just by changing the input types to the source code. Now we can actually check whether it works by comparing the results of the addition that we did on the CPU to the one that we did on the GPU. But to compare them, we have to copy the results from the GPU back into host memory so we can actually do the comparison. So again, you can use this array, basically convert it to an array by taking the C on the GPU and then putting it back into host memory. So this is just a copy. And then you can use the isApprox function to check whether they're correct. And you can see here, it's actually wrong. So let's work out why it's wrong by running and copy back. Okay, all right, rerunning everything, it worked, it was fine. So yeah, this basically means that you can offload safely to the GPU. We use this isApprox function because the floating point math might be a bit different to how it works on the GPU to how it works on the CPU. So you might get very slightly different results. So they probably won't be exactly equal, but they'll be approximately equal. Okay, so yeah, I'll do a quick speed comparison. I'll just run this first so we don't have to wait for all of the results. But this is essentially the same example, but instead of doing a vector addition, we're just multiplying 2 matrices by each other and storing it in another matrix. So the linear algebra base library package provides this function, molbang, which basically says do like times A and B together and store the result in C, where C comes first. Okay, so if we benchmark the first example and then the second example, we'll see one important factor that comes into when you're actually programming with a GPU. Okay, so this might take a long time to benchmark, but we can see it takes around 135 milliseconds on the CPU to do the matrix multiplication. We've made sure that we're only using one core as well with this set number of threads at the top. But we can see on the GPU, well, for starters, this is a huge range. It goes from 8 microseconds all the way up to 900 microseconds, which is quite a big difference. And the reason is we haven't done our benchmark correctly on purpose, but we haven't done it correctly. So because the GPU is a separate device from the CPU, whenever you want to do work on the GPU, it doesn't make sense to make the CPU just wait around for the results. So whenever you launch work on a GPU, the CPU will just continue processing. So it's kind of like this asynchronous programming. So if you've done the parallel programming workshop, it's like this threads at spawn. It will just start the work on another thread and then just continue with whatever's happening. So in order to time this properly, we have to use this CUDA.at-sync macro to make sure that any work that was launched on the right-hand side of the macro is completed before you exit. So this is just like the synchronization or fetching step that you would do in your sort of normal asynchronous programming.
So when you set this number threads equals 1, so it's on the CPU or on the GPU?
Sorry, which line?
So at the beginning, you set the number threads.
Yeah, this is just for the CPU. That's just for the CPU. CUDA, so I said that this MPAGS function comes from the linear algebra library, but CUDA sort of implements an extension to that, which works with CUDA arrays, okay. Which calls the underlying like BLAS library defined in CUDA itself. So yeah, if we rerun the benchmark with the @sync macro, we should see benchmark timing that makes a lot more sense. So yeah, if you're ever benchmarking some GPU code and it takes far less time than you're expecting, it's probably because all you're doing is timing how long it takes to actually schedule the work on the GPU, not how long it takes to actually execute that work. So yeah, so you can see this is much more sensible. It's between 900 microseconds to about 1.1 millisecond. And you should see this is about 130 times faster than the CPU. So GPUs are really good at this sort of parallel processing, especially with big arrays. So if I just quickly switch back to PowerPoint. So this graph just shows the timing, so the actual timing like in seconds of running just an element-wise vector addition like we showed in the first example. But we changed the number of elements with n on the x-axis. And you can see this flat line for the GPU until we hit around between 100,000 and 1 million elements. This flat line is the time it takes to actually schedule the work on a thread. So you're paying this cost every time. It's like the overhead just for launching this kernel. So for most examples, it only really makes sense to do work on the GPU if you have enough work to give to the GPU to overcome this cost it takes to actually schedule the work there. And this cost is about, I mean, we saw it before, it said about 8 to 10 microseconds. It'll depend on your machine, but in that sort of range. So you want it to be doing at least that much work just to sort of compensate for the overhead. What it also means is you can scale up to a huge number without incurring any additional cost. So for example, it takes the exact same amount of time to do 1,000 elements as it does to do 10,000 elements in this example. So it's quite nice. You get you can go up to higher sizes for practically no cost if the array sizes are still quite small. As another example, if we go to matrix multiplication, which is order n cubed instead, we hit this sort of threshold at which the GPU becomes faster than the CPU a lot earlier for a lot smaller matrix sizes. Because matrix multiplications are much bigger operations, you're doing more computation. So here as soon as we're hitting around 100 elements, like 100 by 100 matrices, the GPU becomes a lot better. And by the time we get to like 10,000 by 10,000 matrices, the GPU, at least on this machine, is about 200 times faster than the CPU. It will saturate when the GPU sort of runs out of more cores to process the matrix itself. So yeah, GPUs can be very fast as long as you give it enough work to do at a time. But there are a few extra things that you can do. You don't just have to do like vector addition and matrix multiplication, and we'll take a quick look at those. So remember before I showed in one of the previous lectures a random walk. So you just have a point in space and you randomly move in some direction. The specifics aren't important. What is important is we can define a function in Julia to perform this that will work on the CPU. So this is your custom code itself, and you can write a function that will generate n number of these walks. Just perform it many times. And here I'm just using some broadcast notation to save me having to write a for loop. And so we can give some parameters and call this code. We can, for example, find out the average end position of one of these walks. Obviously, it depends on your application as to what you want to compute. But let's say we actually wanted to take this process and move it onto the GPU instead. So instead of having to completely rewrite our code to make use of the GPU, we only rewrite a little part of the code itself. So for the GPU version, I'll remove this space so we can compare. So in the CPU version, we created an array to store all of the values of our walks, so the positions themselves. So the positions themselves. And then we actually perform the walk, storing the results in this walks array. And here, instead of creating an array on the CPU, we just create an array on the GPU using the GPU array type. So these lines are the same apart from the type. Nothing has changed. The next line is identical, is exactly the same code. The only thing that's changed is you're using a broadcast operation, but you're storing the results in a GPU array. So this basically tells the compiler to use the GPU code to execute it instead of the CPU code. This random walk function is the same function that we specified in our native pure Julia code. So if we define this function and run it, it might take a while to compute the first time, but it runs perfectly. So we didn't change the vast majority of our simulation, we just changed some of the types, and it was able to compile it and run it on the GPU. And again, CUDA.jl gives implementations for reductions as well. So you can write your own reduction. You can write your own reduction to sort of use all your code very generically. So if you write your functions with broadcasts, reductions, maps, sort of the very sort of general generic versions, then perhaps all you have to do is change the types and your code will probably work on a GPU. So this is your sort of your first port of call when you want to get something running on the GPU. Write in this sort of generic vectorized NumPy-like form, and you should be able to quite easily transfer to a GPU. It won't work for everything, which is why we have another session on Thursday to go over the edge cases. I will very quickly go over this example. So in the previous lectures, we talked about estimating pi by throwing darts on a dartboard and measuring or counting the number of darts that hit inside a circle as opposed to sort of outside in the square regions. So yeah, just in case some people missed it. So you have a circle whose edges just touch a unit square, or you have a unit. You have a unit circle and put a square just on the outside, and you randomly throw darts inside, and you count how many land inside the circle, as opposed to landing outside. And the sort of ratios of this, you can estimate pi. Yeah, so this is some very reduced code to do that on the CPU, just one core. And again, our function for actually throwing the dart is just written in pure Julia. And you can see this takes maybe around 4.5 milliseconds when we benchmark it. When we go to the GPU, again, I'll get rid of this side. So this was our CPU implementation, and this is our GPU implementation. Here, we can't quite do the same thing just using the generic functions. So instead, what we've done is just created an array to store whether a dart is hit or not. So just a bool, yes or no. And we calculate that first. So we throw all the darts, we'll get a series of zeros and ones back in an array. And then we'll use the reduction function again to basically count how many hit and how many didn't hit. Anyone want to have a guess at what this line does? It's unsafe free, and you pass it an array. If anyone's done C before, this should look somewhat familiar. No, that's fine. So this first line, what we're doing is allocating an array on the GPU. So we say we want to...
No, I'm just talking to myself.
No problem, no problem. So yeah, so we're allocating some array to store all of these 0 and 1 values. But afterwards, we're not actually using it. We're allocating it and never using it again afterwards. So CUDA provides this function unsafe free, which basically says we're not going to use this memory anymore. Feel free to use it to allow it to be used for another purpose later on. It's called unsafe because if you are using that memory again afterwards, you'll get some memory corruption, potentially. So when you're writing in C, every time you allocate memory, you should also free the memory as well when you're not using it. In Julia, we use a garbage collector, and CUDA does implement some garbage collection for CUDA, but it's not very good, and it doesn't always work. And so this gives you a bit more freedom as to when you are going to use memory and not going to use memory. So it avoids some GC pressure, which can also help performance as well. I should also mention at this point is GPU memory is usually a lot less than main memory. So most consumer GPU cards nowadays would have between like 4 and 12 gigabytes of RAM, whereas it's pretty easy to find a computer nowadays with 32 to 256 gigabytes of RAM. So RAM is much more of a precious resource on a GPU than it is on a CPU. So you should be careful about what you're allocating and what you're not allocating. So I bring up this example as a way that you have to sort of bend your algorithm a little bit to work with this sort of generic GPU interface. So here we didn't have to allocate any memory at all, whereas here we had to allocate some memory and then do another calculation on that memory. If we're writing our own kernels, we can avoid this. And so we'll talk about that next week. Again, a kernel is just a program that runs on the GPU. There's nothing special to the name at all. That's just the language that they use to talk about it. And so when we're actually, yeah, I should also benchmark this code. So when you're running some program that runs on the GPU, we say you're launching a kernel. And so that will take some time. And so launching a kernel has some overhead. But you can see in this case, even though we're allocating a huge array on the GPU is just so much faster at this parallel processing that we get a huge speed up. So we went from, 4,500 microseconds down to 54 or 55 microseconds. So there's about an 80 times speed up, even though we're allocating this big array for this example. So allocation sometimes isn't bad if it gives you your results correctly, and it's good enough in this case. So this is all well and good, but there are some restrictions in how you write your code. So when we spoke about optimization in the past, we spoke about type safety is very important. Type safety and why it's very important in Julia. So type safety is just the compiler knows what type everything is. And so usually in Julia, we don't say what the specific types of things are. We let the compiler work it out. But there are ways in which we can program to be careful to make sure that it's predictable. So here's an example of a function that sort of returns two different values. And this is really easy to do, just saying like 0 or like 1.0, or maybe it's like 1.5 or something. What we're actually saying is, depending on some runtime value of x, because the compiler doesn't know what value is stored within x when it compiles, it just knows potentially that it's a float or an integer or something along those lines, either return an int or a float, because we've written 1.0 instead of just 1. So if we use the code warn type macro, usually you can see if something is type safe if there is a big sort of red highlighted section that says union of, in this case, float 64 or int 64. So this is basically saying that this function will return one of those types of values. And if we have created a GPU array, and what we want to do is basically perform a map. So we map using this type unstable function, each element of this A into another matrix B. So this would be, a vector B, which would have values of either 0 or 1. If we actually run this, we get an error. And the error that comes out says that the broadcast resulted in non-concrete element type real. So that basically says it couldn't infer what the return type was. And specifically, it wants a concrete return type. So this is something that's at the bottom of the inheritance hierarchy, or the type hierarchy in Julia. So these are your ints, your floats, your bools, not like real values or numbers, which is an abstract type. So the way we fix this is, again, you should do this for optimization purposes anyway, is just make sure your code is type safe. So if we change this to instead only return floats, so either 0.0 or 1.0, we can see it's now type safe. The compiler can infer that you're getting a float out of this, and then you can use it on the GPU just fine. And everything works exactly the way you expect. There is one sort of final thing that you'll run into a lot in your code. At the start, I said to you that writing your code in the broadcast vectorized notation and writing it in a for loop makes no difference in Julia. That's only true for the CPU. On the GPU, it won't let you do that. So if I sort of run this function, or create this function, which just tries to sum up all of the elements in an array, and I pass into it a GPU array. Code. If I pass into it a GPU array, it does work here, but it gives me a big warning, and it says that you're performing scalar indexing. So scalar indexing is when you have the array and you actually index and take one or maybe a few values out. And it basically says, don't do this for performance reasons. And the main reason is you're not executing this code on the GPU. This code is running on the CPU. But what happens is when you try and index the GPU array, it says, oh, okay, I have to ask the GPU what was the value of this array at this index. And then the CPU goes and fetches that value from the GPU, goes all the way back to the CPU, and then gets processed afterwards, which is a huge latency. And this happens every single time for each of the elements in your array. So usually what I would recommend is there's a function called CUDA.allow scalar, if you set that to false, if you try to run this function, it will actually give you an error saying scalar indexing is disallowed, because almost 99% of the time, you don't want this to happen in your code. You're moving to the GPU to try and accelerate your code, not make it even slower. Sometimes you might want it, so you can use an annotation, again from the CUDA package, called allow scalar. And so now you can index into that array just fine.
This is on GPU, indexing on the GPU.
So this runs on the CPU, but when you get the value of the index, it will ask the GPU what is that value and then send it back to the CPU. Yeah, so that trip, the latency that it takes to get from the CPU all the way to the GPU and back is incredibly high instead of just going into memory.
Is there any way I can copy this GPU array back to a CPU array?
So yeah, a lot of the time, if you have a sort of small array back, where it's faster to just do the operations on the GPU, you can, for example, copy it and you just convert it to a normal array type. So you can convert it there, and then this B CPU you can use as normal. You can use your for loops and everything. So yeah, basically the conclusion is anytime you're doing the scalar indexing, so a for loop, your GPU code probably won't work, unfortunately. So if you're trying to write code that will work with GPUs and CPUs at the same time, if you can write it with broadcasting, do. Write all of your stuff in like the broadcast notation, use map, reduce, map, reduce as functions, and it should work for both. And all you do is change your input types, and you'll get implementations that are correct for CPU and GPU. In the cases where you can't, and you actually need these indexing in some way, you can write your own custom kernel, and we'll talk about that more next week. So if I go back to here, I'll just sort of summarize what we've seen in the examples. So big one is scalar indexing is very slow. And so you don't want to be transferring data between the CPU and the GPU for each element of your array. If you need to do it in some way, it's better to do what you suggested and copy the array back to the CPU and then do all the processing there.
Copying, that doesn't destroy the GPU array, right?
No, copying doesn't destroy the array. It stays on the device memory there. But if you change it on the CPU, then the device memory will be unchanged. So you won't. The only way you can see those changes if you copy it back.
I see.
So yeah, the way to avoid the scalar indexing, if you're trying to stick with the very sort of high-level array-based programming, is avoid using the for loops in your code if possible. Switch to the broadcasting notation and use these sort of generic functions, as I listed before. Again, if you're doing any computation on the GPU, the memory that you're operating on needs to exist on the GPU first. Essentially, this means creating your GPU arrays, and if you want sort of high performance, instead of allocating an array every time you want to do an operation, you can use these in-place operations, so like molbang, the broadcasting dot equals, to avoid having to allocate a lot and copy data around a lot as well. Usually what happens is in a pipeline is you create your data, possibly on the CPU, copy it to the GPU, and then keep as many of your operations there as possible, instead of having to copy back and forth. That's sort of your last resort strategy, is you want to avoid having to copy back and forth between them. Again, any functions that you use must be type stable as well to be able to compile to the GPU. We'll talk about this a bit more on Thursday as well. Yeah, for now, just use this code warn type macro. You probably get into the habit of using it anyway for your normal code, because it's also good for CPU performance to make sure everything's type safe. Okay, so if we want to go to sort of generic, so being able to do as much as possible on the GPU. Again, we can use the sort of generic functions, that's fine. But if we do need this sort of more complex behavior that you can't easily achieve with broadcasting, you can write your own kernel. We'll go over exactly what that means next time, but this is essentially mimicking how you would write code for the GPU in a language like C that doesn't have this sort of very nice high-level array-based API that you can use to make your code very generic. Yeah, I didn't go into too much detail about this, but we wrote our own native Julia code, and that got compiled into something that ran on the GPU. So it's already generating these kernels for you from the GPU code, but in a very specific way that fits with like map, broadcast, reduce, all of these things. But that's the sort of high-level wrapper around actual real kernels. So we'll talk about that next time. Yeah, there are some packages that will go over making this kernel writing process a bit easier, and it also lets you write kernels that will work on CPUs, GPUs of different brands as well. So like NVIDIA, AMD, Intel, etc. So if you do need to get into that, it's worth looking at some of these other packages. Okay, just to finish, I've already put up the final assignment. Again, just to reiterate, because not everyone has access to a GPU, this won't be marked and counted towards passing the module. So it's only if you want to do it and have some practice. But the sort of task is to visualize the Julia set. Thought would be appropriate for this module. Essentially, is to come up with this sort of visualization. So for each pixel, you do some mathematics to calculate what the color of that pixel should be. The assignment already has an implementation that works on the CPU, and the idea is to just port that to GPU code instead. Okay, that is everything. Are there any questions?